There we go. All right. Chapter 3 is all about exponentials and logarithms and growth and decay, and there's some real-world application problems and all kinds of fun stuff. But for today, for the first bit of 3.1, we are just going to be analyzing exponential functions and then identifying transformations of exponential functions. So basically what we're doing is we're taking everything that we've already applied to polynomials and rational functions and radical functions and all that stuff, and we're extending it to exponential functions. So we're going to talk about domain, range, growth, decrease, or increase, decrease, which will be called growth and decay when we talk exponential. And then we're going to talk transforming those functions, moving them left to right, reflecting them over axes, shrinking them, expanding them, things like that. So a lot of it's stuff that we've done with other types of functions already. We're just including exponentials now in that. So grab whatever it is you're using to take notes and let's get going. All right. This pen works. 3.1 exponential functions. Okay. So an exponential function is any function that can be written as f of x equals a times b to the x. So if x is in the exponent, it's an exponential function. And in this case, a and b are constants. And a is not equal to 0. And b is greater than 0, and b is also not equal to 1. Because if you think about it, if b was 1, 1 to any power is 1, so that doesn't count as an exponential function. Okay. So b has to be greater than 0 and not equal to 1. A has to be not equal to 0. Okay, so then we have words to describe whether it's exponential or if it's increasing or decreasing. So it's exponential growth if it's increasing. And that would be if b is greater than 1. And this is what our exponential growth typically ends up looking like, something in this format where it starts off growing slowly and grows faster and faster as time goes on. And then the other version is exponential decay. And that's if b is between 0 and 1. And generic exponential decay looks something like that, where it decays quickly and then decays slower and slower and slower, but it's still decreasing the entire time. So exponential functions don't change between increasing and decreasing. They're either increasing the whole time or they're decreasing the whole time. Okay. So, for example, we could have f of x equals 1/2 to the x. All right, and so we're going to go over some of the things that we want to know given an exponential function like this. So the first thing that I would probably do is graph it and see what that looks like. So I would go grab Desmos, and we'd go 1/2 to the x and take a look at what happens there. So some important things that we might want to notice. We notice that this whole thing sits above the x-axis. We also might notice that Although it might kind of look like there's an asymptote vertically, there's not. It does continue. You could plug in any value for x, and it still works out in the function just fine. But it also never gets to 0. So it does have a horizontal asymptote, but it doesn't have a vertical one. We notice that it crosses the x or the y-axis at 0, 1. So that's another thing that we want to kind of emphasize in our graph. So if I was going to graph this, or if I was going to draw a quick sketch of it, we might have something like this. I would put down where it crosses the y-axis. I would draw something like that. It's pretty good for a quick sketch. And then we'd want to put down things like we'd be asked for the domain. For exponential functions like this, our domain is just the standard domain, negative to positive infinity. The range, however, is restricted because this thing is never going to be less than 0 or equal to 0. So the range is going to be from 0 to positive infinity since it's above the axis. That's where if you see something like this being shifted up or down, the range changes. So if this is vertically shifted at all, if it's shifted up, then your range is more limited. If it's shifted down, then your range is expanded a little bit. If we're asked for increase and decrease, well, that's easy for this one. This is never increasing. There is no interval of increase. But decrease, it's always decreasing. So we would just put negative to positive infinity. This thing is decreasing the entire time. We might be asked for, let's see, an asymptote. In this case, this one does have an asymptote at y equals 0, or the x-axis. And that's kind of the standard asymptote for an exponential function. But again, if it's shifted up or down, then that asymptote very well may change. And then also we might be asked what the intercepts are. So we might be asked for the y-intercept or the x-intercept. In this case, the only one that would make sense to ask for is the y-intercept because that's the only one that there is. And so we would say that the y-intercept is at 0, 1. Or you could just say at 1 because by definition, a y-intercept, the x value is 0. We also will likely be asked about the end behavior. So we have to remember our limit notation for end behavior and all of that. The limit as x goes to infinity of f of x, and the limit as x goes to negative infinity of f of x. So in this case, the right arrow is going to 0. It's got that asymptote at 0. It's approaching 0. The left arrow, though, is going off to positive infinity. So that would be our limit as x goes to negative infinity. The function is going to positive infinity. And that is pretty much everything that you could want to know about a function like this, an exponential function. Okay. So again, we'd be asked for domain and range. We could be asked for increase and decrease, for asymptotes, the y-intercept, and the end behavior. Those would be some common things we might be asked for. And that's just like any other function that we've been looking at so far. We've looked at all of these things before, so hopefully it's just now we're just applying it to a new graph. Any questions on this first example? Okay, thanks, Paige. Yeah, any questions so far? any numbers we're not sure where they came from, any limits or anything that we're not sure why that's the case. Okay. If you do have any questions, feel free to unmute yourself and say so, or type in the chat. Okay. So that's one sort of thing that we'll be asked to do, just analyze the function. The second thing we'll be asked is about transformations. Okay. So we'll be given a parent function and then a function that's become transformed. And we'll be asked what kind of transformation happened. So for example, if we have f of x is e to the x, this is going to be one of the most common exponential functions that you'll deal with in this class, and then also in calculus, you'll have a lot of exponential e to the x functions that you're going to work with. So this is a good one to become familiar with. And so we'll be definitely becoming familiar with this throughout this whole chapter. So if f of x is e to the x and g of x is, we'll say, negative e to the x plus 3 minus 7. So this is going to introduce some of our transformations here. And the transformations work pretty much the same way as transformations did for any of our other parent functions, for our quadratics and cubics and absolute value functions and all of that. It pretty much works the same way. For example, the minus 7 moves this thing down 7. The plus 3 moves this thing left 3. So if it's up in the exponent with the x, that's moving it left to right. If it's not up in the exponent, it's moving it up and down. And then the negative is reflecting it over the x-axis. Since it's a negative outside with the y, the negative is not up in the exponent. So this reflects over x-axis. So those are all the transformations that's happening with that one. Okay. So there's one example. All right. And then I'm going to use another example to talk about the other things that can happen with it. This time we'll say f of x is 1/2 to the x. And g of x is 3 times 1/2 to the negative x plus 1. Okay. So just like with our other functions, when we had like a quadratic or a cubic or anything that's out in front of it is vertically stretching it or shrinking it. If it was something multiplied up with the x, then it would be horizontally stretching or shrinking. But down here we have vertical stretch. Vertical stretch. And then in order to deal with what we have going on up here, whenever you have a coefficient in front of the x, a rule of thumb here is to undistribute it. If it's something that's already distributed through, you want to undistribute it so that you can clearly see what's going on with which direction this thing is moving and all that stuff. So to undistribute this, there's a -1 in front of the x, an implied -1. So I'd go -1 times x minus 1. That's undistributing the -1. Because then I can use that to notice, okay, we are going right 1 because of the x minus 1 here. And then it's also being reflected over the y-axis. Because of that negative. Okay. So here we have vertical stretch. It's being moved right 1, and it's being reflected over the y-axis. So kind of the rule of thumb, anytime you have a coefficient in front of x, factor it out or undistribute it. Okay. Any questions with either of these two so far? Any numbers we're not sure where they came from? Any steps we're not sure what happened there? Okay. Then I'm going to give you guys a couple transformation ones to try. I will try to leave this here for reference. All right, so there's two for you guys to try. So try and figure out what the transformation is for this one and for this one. And when you think you've got it, type trick or treat into the chat. All right, as people finish, I'll start with this one up here. We have vertical compression by 1/2. We have that we're moving right 4 and up 7. So if you did things correctly, Those are the three things we should have identified on that top one. All right. Let's see. For the second one, in the chat, what's one thing that's going on with that? All right, down 4. That's 1. What else? Does it help if we factor out the 2 there? That gives us 2x plus 1/2. Is this going to be vertical or horizontal that we're dealing with here? And then is it compression or stretching? What do we think? Close. It is horizontal. Or actually, you're right. It is, sorry, it's compression. Yeah. Yeah, so just like with, I'm gonna move that piece of paper. So just like when we had things with quadratics and stuff like that, where the number inside with the x was greater than 1, that was horizontal compression. If it was less than 1, or between 0 and 1, then it was horizontal stretching. So this is horizontal compression here. And then the plus 1/2 is just telling us that it's going left 1/2. All right, so that's the trickiest one there, identifying the horizontal component, just because you do have to factor something out a lot of the time. Sometimes it will be written nicely and written already in this format for you, in which case you can just directly identify it, but sometimes it won't be, and so we want to be able to recognize that as well. Okay. So those are the main things that we need to know how to do for today. Any questions on any of the examples that we've done so far? Okay. If not, then we can kind of start moving towards the assignment here. First thing, if you have not finished your quiz, make sure that's your first order of business today. Finish your quiz and turn that in. Second order of business is the homework assignment itself, which I have just posted. Today is a worksheet. Tomorrow we will have IXL, and we're kind of sort of going to be alternating between IXL and worksheets for this chapter, depending on if I liked the IXL sections or not for this chapter. So here's our worksheet. Part of it's kind of handwritten. So the first 2 are analyzing the graph of the function. Make sure you read all of this. We want to describe domain, range, x, y intercepts, depending on which it has or if it has both, asymptotes, end behavior, and then increase or decrease. So make sure you plot those in Desmos or with your graphing calculator to get an idea of what the graph is looking like, and then do your analysis from there. Then the transformation from f of x to g of x. So this is the same kind of thing that we were just doing with our examples. You have the original function and you have the transformation, and then you have to say what happened. The last 2 actually, we are going to wait on until tomorrow. So only do 1 through 7 today. This 3 and 4, you're welcome to try if you would like to, but they are not going to be required for this assignment because we have not gotten to that point yet. That's what we're talking about tomorrow. So again, feel free to try these if you want to, but 1 through 7 is the real requirement for today. Let's see, how do we know if something is vertical or horizontal compression? Yeah, that's a great question. So vertical versus horizontal. So horizontal has to do with when it's up in the exponent with the x. So if it's something that's multiplied by the x within the exponent, then that would be horizontal compression or stretching. And then vertical is when it's outside in front and it's not up with the x. So for example, if we had 1/3 e to the x, this would be vertical compression. But if we had 3 e to the x, this would be vertical stretch. And then if we had something like e to the 3x, that would be horizontal compression. Or e to the 1/3 x would be horizontal stretch. So those are the differences there. Yeah, no problem. Okay. Any other questions, comments, concerns? If not, you are free to go start working on stuff. If you do have questions or anything like that, feel free to stick around. I think that is everything. Remember, if you don't have your quiz done, that's the first thing you need to do.